standing waves and the resonant modes of vibration of a string rigidly attached at two ends, and from that we also saw the formula for energy of a standing wave when it is in a resonant mode like that. Okay, so we will continue from that point onwards, couple of more types of cases to discuss, and then we'll come straight to the doubts and questions. So today most of the time I intend to discuss doubts and questions, but just this last portion of theory regarding standing waves, let us complete it. Okay, so now let us look at the second type of standing waves from resonant modes. This time when the string is such that it has a rigid boundary on one end and a flexible boundary at the other end. Okay, so it's slightly different situation compared to the last time. So resonant modes of vibration for a string with one end rigidly attached and the other end flexible. So the physical example of this situation is this: when we have kind of condition like this, this is a wall and this is acting like a rigid boundary, but on the other side we have that condition, it's a smooth fixed pole and there is a ring attached, okay, which can slip freely on that pole. So as a result of that, what happens is this boundary of the string or this end of the string becomes a flexible, okay, boundary, or what we also used to call a soft boundary, and this is a rigid or a hard boundary. So pulses, as they reflect back and forth from here, there is phase inversion and there's no displacement at this point because it's like a nodal point, and this becomes like a anti-nodal kind of point. So that kind of situation. So the string's length is L, the tension in it is T, and the mass per unit length is M. So the end A will be a node for the standing wave pattern, whereas the end B will be an antinode. Okay, for the standing wave pattern. So just make a quick note of this, then we'll look at the harmonic modes. So this is within the topic of standing waves. Okay, written this down, people. Aditya, open and closed organ pipe, actually organ pipe refers to sound waves, so that will come in the next chapter. But yes, the kind of standing waves created over here is very similar to the corresponding pressure waves or longitudinal standing waves which are created in the case of open organ pipe, or rather closed organ pipe. Okay, one end is closed and one end is open, so that type of organ pipe is called closed organ pipe, but that will come in the chapter of sound. So in transverse waves, the standing waves are only possible in this kind of situation where a thread has got two boundaries on either end. So one end, either both ends are rigid, or one end is flexible and the other end is rigid, or it can even be a situation where both ends are flexible. Even that is possible. Okay. So anyway, let's understand what kind of modes are possible over here. So harmonic modes of vibration, or what we call the natural resonant modes of standing waves. So in this case, they will always have to be such that this end A is a node and the other end B is an antinode. So as far as the fundamental mode is concerned, the fundamental mode always corresponds to minimum frequency and therefore maximum wavelength. So there should be least number of nodes and antinodes in the fundamental mode. So least number of nodes and antinodes means in this particular case, there'll be one node and one antinode. So the string will vibrate in this kind of a way, that it's vibrating between these two positions, where this end is an antinode and this end is a node. So the length of the string here actually becomes lambda by 4. That is the distance between two immediately consecutive nodes and antinodes. So for the fundamental frequency case, the wavelength is equal to 2L. So the frequency is now given by this formula, 1 by 4L square root of T by mu. So as you can see, it is a different formula for fundamental frequency compared to a string which is tied at both ends. A string which is rigidly tied at both ends, that one's fundamental looks like this. And what happens over there is there are two nodes and one antinode. So lambda by 2 is equal to L in this kind of a case. I'm just showing you as a comparison. So here the fundamental frequency formula is 1 by 2L square root T by mu. Here the fundamental frequency formula is given by this. Okay. Now likewise, you will understand the first overtone is the next possible case for low frequency. The next lowest frequency possible is when you have the next lowest number of nodes and antinodes. So that will be called the first overtone mode. In the first overtone mode, the string will be vibrating in some kind of a situation like this. This happens. Okay. So in fact, this is more like this. Okay. So we have nodes and antinodes like this. So this is lambda by 2 and another lambda by 4. So the total length becomes lambda by 2 plus lambda by 4, or 3 lambda by 4. So in the first overtone mode, lambda, as you can see, becomes from there. Sorry, here it was 4L, my mistake. Lambda by 4 is L, no? So lambda is 4L. And here becomes 3 lambda by 4 becomes L. So lambda becomes 4L by 3. So correspondingly, the frequency becomes 3 by 4L square root T by mu. So here the frequency of the first overtone is in fact the third harmonic. And we say that the second harmonic does not exist. So in this case, the first overtone mode has a frequency equal to the third multiple. So that is called the third harmonic of the fundamental. Okay. And in this case, the second harmonic therefore does not exist in the standing wave pattern. You cannot create a second harmonic in this situation. Okay. So again, if you were to compare this situation with the situation where the string is tied at both the ends, there the second overtone looks like this. So in the second overtone mode over there, I mean first overtone mode over there, it was 2 times f naught because lambda became equal to L. So f1 became 1 by L square root T by mu. So the first overtone was the second harmonic, but here the second harmonic does not exist. The first overtone is straight away the third harmonic after the fundamental. So if this frequency, for example, is 100 hertz, then the next lowest frequency at which it can vibrate is 300 hertz. It cannot vibrate at 200. So this is very important to remember that when the boundaries of the string, either end of the string are opposite in nature, that is one is hard, the other is soft, then only the odd harmonics exist. We will see this series as it goes along. You'll see only the odd harmonic terms exist. So first overtone will be third harmonic, second overtone will be fifth harmonic. So the series will be f naught, 3 f naught, 5 f naught, 7 f naught, like that. So odd harmonics only will exist. Whereas when both the boundaries are like, that is either both the boundaries are hard, like the one we discussed in the first case, or both boundaries can be flexible also. But in both these cases where the boundaries are same type, there will be all harmonics, both even and odd. And the series will be of the type where the nth overtone is the n plus 1th harmonic. Yeah, lambda is equal to 4L. That correction, sure you make it over here. And similarly here lambda becomes 4L by 3 because of this. So like that, now you can understand yourself that if you were to look at the other overtones, like the second overtone, the third overtone, etc., this series would continue in that manner that only the odd harmonic terms are allowed, or only the odd harmonic terms exist in the resonant modes. So your second overtone mode, where the frequency will write as f2, that situation will look like this. 3 nodes, 3 antinodes. 2.5 loops. You can think of it like that. The fundamental is half a loop. The first overtone is 1.5 loops. The second overtone is 2.5 loops. So L becomes 1/2 loop plus 1/2 loop plus 1/4 loop. So 5 lambda by 4. So in this case, lambda becomes 4L by 5. And accordingly, the frequency therefore becomes 5 by 4L square root T by mu. So you can see that the second overtone is the fifth harmonic of the fundamental. Likewise, when it comes to the third overtone mode, be like this. So it will be 3.5 loops. So like that, when we generalize for the nth overtone mode, the length of the string will occupy or will be occupied by n full loops plus one half loop. So accordingly, lambda will become 4L upon 2n plus 1. So the frequency of the nth overtone will become 2n plus 1 times f naught. So this is a harmonic series where f naught is 1 by 4L square root t by mu. F1 is 3 f naught. F2 is 5 f naught. F3 is 7 f naught. F4 is 9 f naught. And like that, the nth overtone is the 2n plus 1th harmonic. Has a frequency equal to 2n plus 1th harmonic of the fundamental. Okay, so this is the simple thing to remember about this kind of situation. Okay, so I hope this is clear to all of you people. Okay, so the thing you need to remember is very simple, that if both the boundaries are rigid boundaries, then your series is of that type, that Fn is n plus 1 f naught, or the nth overtone is n plus 1th harmonic. Whereas if they are opposite boundaries, one is rigid and one is soft, then it is this kind of odd harmonic series, that the nth overtone is 2n plus 1th harmonic. Okay, and in fact, this simple rule of thumb will come in very handy when we look at longitudinal harmonic waves also, or sound waves, standing wave in the case of sound also in the next chapter. So it'll be, you'll see it's correspondingly an identical concept. The only difference is there, the type of wave we are talking about is pressure wave or longitudinal displacement waves, whereas this is transverse waves on a string. Okay, so let's look at simple question or two. So, for example, at the very basic level, we can have a question like this: that, for example, suppose okay, just try out this question. This is a very basic, absolute, simple level question. It's just to do with the fact that the harmonic series is this odd harmonic series. Yeah, Ashwin, that's correct. All right. So as usual, you have to consider here that the three frequencies are odd multiples of some kind of fundamental frequency. So keeping in mind that they're odd multiples of a fundamental frequency, you have to find that kind of common factor and then find the highest one among that. Okay. So 140, for example, can be written as 7 into 2 into, rather, it can be written as 7, 5, 2. Okay. Now this has got to be odd multiple of some kind of fundamental. So that fundamental could be 20 hertz, in which case that odd multiple is, or in which case this particular frequency, let's say this is FA. So in that case, FA is equal to 7 F naught. Okay. Or the fundamental frequency on the other hand could be also be, for example, 28 hertz, in which case FA is 5 F naught. Okay. But then you'll have to see whether the other ones can correspond to that also. Okay. And these are the only possibilities over here, because any other combination you will see it will become an even multiple. So even multiple is not possible. Then similarly, FB, suppose that is 300. So 300 can be written as, uh, again, if you were to factorize it that way. Okay. So for example, it can be written as 15 into 20. Okay. Or it can also be written as 5 into 60, or it can also be written as 3 into 100. Okay. Or it can also be written, for example, as, yeah, I think that's it. Yeah. So you can see that the possible fundamental frequencies for this are 20, 60, and 100. But the only one that matches with this is 20. So we'll have to take F naught as 20, in which case this FB becomes 15 times F naught. And similarly, the third one, which was 520. Okay. No, so these are not having common. These are not having common. We'll have to change this one. Just a second. In fact, these terms cannot be multiples of any common frequency. Hope you're understanding the point here. No? So 520 cannot be a member of this series. So let us say we've got something else, like we've got 540. Oh, now this will work. So 540 can be written as 27 into 20. So this is fine. Okay, that can also be written as 9 into 60, or it can also be written as 6 into 9. No, that's it. So these are the two possible. Okay, so for example, if these two had been the only ones, then the f0 could have been 60, or the f0 could have been 20. Okay, so in that case 60 would have been the maximum. But for example, for this and this, the common values of f0 are only 20. Okay, and again for fa and fc also, the common values are only 20. So here actually there's only one distinct fundamental frequency possible. Okay, there's a unique value. So for 140, 300 and 540 to be odd harmonics of some fundamental, there's only a unique value of fundamental possible. f0 is equal to 20 hertz is the unique case. Okay, so in fact this question is even better that way, because it's not a question of maximum possible frequency, it is the only possible common frequency. Whereas for example, if I had only 140 and this one 300, then f0 could have been only 20 hertz again. Okay, and if I had for example 300 and 540, then f0 could have been 60, or it could have even been 20, because 300 can be written as 5 into 60, and 540 can be written as 9 into 60, and also 300 can be written as 15 into 20, and 540 can be written as 27 into 20. So these could have been the 15th. Okay, so accordingly this could have been possible such that this would have been a case where this is fifth harmonic, so it is the second overtone. Okay, and this is ninth, so that would have been the fourth overtone. f4 would have been 540, which is 9 f0, for f0 to be 60 hertz. Whereas in this case 300 would have been 15, so that is seventh overtone, 15th harmonic. Okay, and this would have been 13th overtone, or 27th harmonic, had f0 been 20 hertz. But as it turns out, we are discussing the case where all three are the case. So in this case, the fundamental is 20 hertz. So 140 hertz is the seventh harmonic, which means it is the third overtone. Okay. And 300 is the 15th harmonic, which means it is the seventh overtone. Okay, and likewise 540 is the 27th harmonic, which means that it is the 13th overtone. Okay, so basically this series is like this: f0 is 20, f1 is 60, f2 is 100, f3 is 140, f4 is 180. Okay, like that. F5 is 220. F6 is 260. F7 is 300. And like that the series goes. Okay, people. So just minimizing this a bit, make sure you understand this. So this is a little bit like, application of number theory kind of concept. Very basic number theory, nothing extraordinary. Odd number, even number, multiples kind of things. Okay, next up, let us look at a question with more things about the equation of standing wave and all that. Okay, so we'll do a question similar to one we had done last time, but with both the boundaries being rigid. So the tension in the string T is, let us say, 1000 newtons, and the linear mass density is, let us say, 2.5 grams per centimeter. Okay, and the length, let us say, is it's a smooth rod, and this is a ring which can slip freely and all that. Okay, so if the string above is vibrating in its second overtone mode, okay, with amplitude at the antinodes equal to 2 millimeter, okay, take EB as your x-axis with the point A as your origin, okay, and assume all particles are at mean position at t equal to 0. Okay. And write the equation of the standing wave. Okay. Find its wavelength and frequency. I mean, when you write the equation, everything should be in numerical terms. K, omega, all these things. Okay. And secondly, what is the phase difference of vibrations between pair of particles at 10 centimeters and x equal to 30 centimeters. 20 centimeters and x equal to 100 centimeters. Okay. And third, the mechanical energy of vibration in joules. Okay, so this question will give us a idea how to solve any and everything related to standing waves. All aspects of standing waves are more or less covered within this. Just try this out with it. No, gram per centimeter has to be converted to this thing, kg per meter. So 2.5 will be more useful. Oh, sorry. Yeah. Wait. Converted to 0.25. My mistake. It's not 2.5. It's 0.25. So just make a adjustment in the value of this. Okay. All right. So let us look at the calculations. So first of all, we're talking about its second overtone mode. So second overtone mode means that there will be 2.5 loops. So the string in its vibration will look like this. So your L will become 5 lambda by 4, or the wavelength will become 4L by 5. Okay. So your frequency will be fifth harmonic, or so lambda is becoming how much? 48 into 4. Okay. Just check your answers. Yeah. So the frequency will be this type. Okay. So your K, which is 2 pi by lambda, become pi by 0.46 radians per meter, or that's the same thing as pi by 46 radians per centimeter. Okay. And your omega, which is 2 pi f, will become 2000 pi by 9.6, or you can also write that as 1000 pi by 4.8 radians per second. Okay. So now start with the general equation of the wave. So standing wave equation is some maximum amplitude into cos kx plus phi 1, let's say, into sine omega t plus phi 2. Now here x equal to 0 is a node. So cos phi 1 should be 0. So phi 1 will take as pi by 2, and at t equal to 0, y should be 0. So sine phi 2 should be 0. So phi 2 will take as 0. Okay. So y will become 2 millimeters sine kx sine omega t type of term, where you can see that k will be pi by 46 radians per centimeter, and omega can be written in many different ways, but I'm writing it like this: 1000 pi by 4.8 radians per second. Okay. So you can see that the nodes will be at x equal to 0, x equal to 46, x equal to 92 centimeters. And the antinodes will be at x equal to 23, x equal to okay, and x equal to no, I think I've got something wrong over here. Just a moment. I might have made some calculation mistake. I think lambda will come longer than this, no? Because the whole thing is 240 centimeters, and no, it's okay. Lambda is 192. Here I made a mistake. Wait. This is 2 pi by 192, no? Not so. This calculation is wrong. Just a second. The value of k I've written finally is wrong. Lambda is okay. इसका double हो जाएगा actually. Lambda is 1.92, na? So it will be 0.96. Okay, or 96 radians per centimeter. Okay, so just a second. This will be 96. Okay, so this will be at 96 and 192, and this will be at 43. Okay, 139. Something is going wrong. Forty-eight. Sorry. That's a mistake. Okay. So 96 plus 48 will give us and all right. This is correct now. So basically, the string is vibrating such that at t equal to 0, it's at a position like this. Now at quarter of a time period later, it should be at a position like this. So these 3 points are the nodes. So this is 96 centimeters, this is 192 centimeters. Whereas these three in between points are the antinodes, which are at 48, 154 and 240. No, there will be three nodes and three antinodes, no? 144 पे क्यों होगा बेटा? 154 पे होगा ना? 96 plus 48 is 154. Oh, sorry, this is 144. My mistake, not 154. 144. Okay, so these are the antinodes. These are the nodes. Okay, so this is the wave equation. Y is equal to 2 millimeters sine pi by 96x sine. As I said, you can simplify this further, but I have just written it like this: 1000 pi by 4.8. You can divide by 4 and all that, numerator, denominator, doesn't matter. T, where x is in centimeters and t is in seconds. This is the numerical version of the wave equation. Okay, so now you can also see that the pair of points that we were talking about now, 10 and 30, they are located where? They are located between the first two nodes. So that pair of points is here. X equal to 10 is somewhere here. X equal to 30 is somewhere here. So they are in phase. So therefore, particles at x equal to 10 and x equal to 30 are in phase. In fact, you can see from here, the equation for x equal to 10 wala particle is 2 millimeters sine pi upon 9.6. This is its amplitude into sine omega t. So it is some positive of some amplitude into sine omega t. Okay, and that amplitude is equal to this value. Similarly, for the point at x equal to 30, is 2 millimeters sine of pi by, divide this by 3, so 3.2. So again, this is a positive quantity. So it is positive of some other amplitude, let's say amplitude prime. So they have different amplitudes but same phase. But for example, if we consider the particle at x equal to 100, I think that is one of the other ones I've taken, 20 and 100. So the particle at x equal to 20 is here, but the particle at x equal to 100 is over here. It's beyond that node. So that pair is in opposite phase. So particles at x equal to 20 centimeters and x equal to 100 centimeters are in opposite phase. They have a phase difference of pi. You can similarly write the equation and check out. तो जो सेकेंड वाला पार्टिकल है 100 के लिए, उसके लिए क्या होगा? ये जो साइन टर्म है, इट विल बी बिटवीन पाई एंड 2 पाई, so it will be a negative quantity. So that is why. So you will see that you will get for x equal to 20 as some amplitude, let's say a1 sine omega t. But the other one, when you write, you will get it as minus of some amplitude into sine omega t, because that minus a2 will be 2 millimeter into sine 100 by 96 pi. So you can see that this is a negative quantity, this term. This term will become a negative quantity. Okay. So the particle x equal to 100 is present somewhere here. It's very close to the node, so it has a very small amplitude. Particle x equal to 20 is present somewhere over here. It has a comparatively larger amplitude, but more importantly, they are out of phase. When this one is at the positive extreme, this one is at the negative extreme. So they have a phase difference of pi. Okay, so hope this is clear, people. Now moving on to the last part, the energy. That is given by the formula half ka half, 1 by 4 into this thing. That is this kind of thing. This factor half comes because they have, you know, they have variable amplitude. So in this case, it will become 1 by 4 into mu L, so that M, which is mu L, will become 0.25 gram per centimeter into 240 centimeters. Okay, so that will be 0.25 into 240 in grams, and then divide by 1000. So the total mass of the thread will become how much? 0.06 kgs. Okay. Multiplied by that maximum amplitude, which was 2 millimeters, multiplied by omega square. Now omega was 1000 pi by 96, wasn't it? Sorry, by 9.6. So this will be in joules now. Yeah. Into, now this can be written as 10 raised power 6 pi square upon 9.6 square. This will be in joules. So you can take this approximately, take 6 millijoules. So here I've done two approximations. I've taken pi square as approximately 10, and I've taken 9.6 as, square as approximately 100. It's actually 92.16. So I've done a big approximation, but I'm just saying order of magnitude wise, it's like this. This is a huge amount of approximation. Actually, it is around 92.2, but I've approximated it as 100. So energy of a standing wave, remember I told you last time, 1 by 4 linear mass density into the length of that part into omega square into the antinode's amplitude. Okay, and now one more type of question you can be asked over here is more a logical question. I'll just put up that question over here, that at time t equal to 0, okay, which particles, that is in terms of x, have maximum mechanical energy, and what type of energy that is. Okay, and what type, that is kinetic energy or potential energy. And again, one quarter of time period later, which particles have maximum energy and what type of energy. So basically, remember at t equal to 0, all the particles were at mean position. So the string was having energy in what form? Kinetic energy. So which particles have maximum kinetic energy? The ones which are at the antinodes. Whereas quarter of a time period later, it's gone to the maximum stretch position. So the energy is converted to potential energy. And which particles will have maximum potential energy? The ones at the nodes. Okay, and we've already identified the nodes and antinodes before. So that logical kind of thing, it becomes like this. So if you just draw a snapshot picture, you can see that these particles were going up. And these particles were on their way down. And again, this one was going up. Okay. So energy is in the form of kinetic energy. And that is equal to, okay. And particles at antinodes, which was x equal to 48 centimeters, x equal to 144 centimeters, and x equal to 240 centimeters. They have maximum energy in the form of kinetic energy. Okay. See, this is what our nodes, anti-nodes were: 48, 144, and 240. Whereas our nodes were 0, 96, and 192. So this is the snapshot at t equal to 0. Whereas by the time we have come to quarter of a time period, the string has changed shape to this. So now the energy is in the form of maximum potential energy. And that potential energy is present here, here, and here. So it's for these type of logical questions that concept of redistribution of energy or oscillation of energy, etc., is very important. So this is the snapshot picture at 1/4 of a time period later, or you can write it as 1 upon frequency into 4. Okay, people. So as I said, with this we cover all the different types of situations possible for standing waves. Okay, and also all the different types of questions that you can be asked. So this energy calculation kind of question is not there in H.C. Verma, but you will find it in D.C. Pandey or in your this thing module questions. Other than that, there are all types of questions required in H.C. Verma. Okay. So more or less H.C. Verma is a complete thing, but if you supplement it with the module questions, then you are well prepared at the advanced level also. So we'll take a short break, 5 minutes, and we'll continue with more problems. And also whatever doubts you might have, if you have anything, just send me on the chat message. I will discuss with you immediately after the break. Okay. So we'll just take doubts after that. Okay, people, let's resume. So I have received some doubts, short answer questions, then exercise 2, then also HC Verma. Okay, so let us start with exercise 1 and exercise 2. We'll come back to the short questions after that. So just turn to your booklet or base module. Exercise 1 questions 29 and 35. Let's start with these two. Okay, then we'll come to the exercise 2 ones also. So just go through these questions. I'm explaining it in a moment. All right. So have you gone through question 29? Oh, actually, question 29 is air column problem. So this is a sound waves question. Okay, all these organ pipe questions are sound wave based questions. So just leave it out for now. Okay, do it. We'll discuss very soon. But for example, question 19, sonometer experiment. This is based on standing waves in a string. Okay. So these questions, 21 onwards, you leave out because they are to do with sound waves. Okay, beta Aditya, is that clear? Have you done question 19, Aditya, in this exercise? Okay, good. Okay, and what about 35? 35 is also closed organ pipe, so that we will do later. Okay, let's come to your doubts in exercise 2 then. So exercise 2, so these are sound waves problems, so we'll do them later. Exercise 2, question number 11, C option. So wait. Okay, so in question 11, standing waves on a string, the C option says all particles may be at their positive extreme simultaneously once in a time period. So that depends now. I mean, that will happen only if it is in the fundamental mode. Okay, so that's why it's correct to say maybe, because if the string is vibrating in the fundamental mode, then this will happen. No, all the particles are simultaneously at the extreme position. Or even if the string is of this type, vibrating in the fundamental mode, they will be at the positive extreme simultaneously. But if this same string is vibrating in first overtone or any other mode, then all particles will never be at the positive extreme simultaneously. They'll be at extreme simultaneously, but not at the positive. Some at positive, some at negative. Same way here, ऐसा हो जाएगा ना. So that's why 11C option is correct, because it says maybe. So they may be at the positive extreme. That happens in this and this case, but they are not at the positive extreme simultaneously in that case. Okay, then question number 15. The other options are clear, na, in 11th? Okay, so let's come to question 15. Just a moment, yeah. So a clamped string is oscillating in the nth harmonic. Then the total energy will be n squared times the fundamental. Okay, so clamped string here, we'll have to assume it's clamped at both the ends. Excuse me. So the fundamental looks like this. So in the case of fundamental, this is this. So the energy is 1/4 mu L into omega naught. So that will become 4 pi square f naught square into a max square. Okay. Now in the nth harmonic, that will actually be n minus 1th overtone. So let's say okay. So this is a case. So energy will become 1/4 mu L into 4 pi square fn minus 1 square into a max square. Now again in this question there's an assumption that the maximum amplitude or the amplitude of the antinode here is the same thing as the amplitude of the antinode over here. Both the cases the range of motion is the same, but just the differences of the mode. So if you compare these, you can see that this will become this. Okay, so that is nothing but n square. So we can say that the energy of the nth harmonic or n minus 1th overtone will become n squared times E naught, assuming that A max is the same. Okay, so Aditya, I hope this is also clear. Yeah, I'm coming to that, Siddharth. Okay. Exercise 2, right, Siddharth? 19 to 23. Okay, so this formula is clear, no? This formula is coming from this, that energy of any standing wave is given by 1/4 into total mass of this part into omega square into A max square. So in this omega is 2 pi f, where remember f is the modal frequency. No? So f is actually this. Okay. So yes, next we are moving to 19 to 23, that passage. Oh, this is again sound better. But actually you can do it quite easily. इसमें क्या हो रहा है ना कि sound is going in one path along the quarter circle directly to the detector, and along the other path it is going 3/4 of the circle. So the path difference of the sound waves, the delta x, will actually become pi r by 2 or 1 this thing. So if this path difference is lambda by 2, for example, there will be destructive interference. If it is lambda, there will be constructive interference. If it is 3 lambda by 2, there will be destructive interference. So that's the way of doing the question. However, we will discuss it in interference of sound waves. So that passage 19 to 21, it is to do with interference of sound waves. where the concept is the same. The amplitude will add according to this formula. A1 square plus A2 square plus 2 A1 A2 cos delta phi, but only this will be a pressure amplitude instead of a displacement amplitude, and the delta phi in this case will become 2 pi by lambda into path difference. And in this case, the path difference will be the path of the longer one, which is going through 3 by 2 pi r, minus the path of the shorter one, which is going by pi r by 2. So that is how you have to do this question. However, we'll deal with this later. Okay, anything else from the exercises? Otherwise, H.C. Verma, somebody had a doubt? Yeah, Ashwin, question number 55 of H.C. Verma. So just go through H.C. Verma, we'll discuss few questions. 55 is also a problem, I think, which is to do with standing waves where one boundary is flexible and one is rigid. Let me just go through it. Yeah, so H.C. Verma, if you turn to page number 327, Ashani, this one is to do with the water. The one I was talking about is 57th. Okay, we'll do 57th also. But let's look at 56 first. Sorry, 55 first. Okay, so in this, what is happening is you have this kind of a string going around a fixed pulley over here. And you suspended some weight even. This, okay. Of course, some kind of a table kind of thing. Okay. Okay, so now what the question is saying is that the string vibrates in 10th harmonic in unison with a particular tuning fork. So you have a tuning fork whose frequency is F. So that frequency is the 10th harmonic of the fundamental frequency of the string. Okay, so that means it is basically the 9th overtone. So it is basically, if this length is L, tension is T, and tension is obviously in this case equal to the weight. So this is 10 by 2L square root T by mu, or 10 by 2L or 5 by L, whatever, square root of mg by mu. And that is the frequency of the tuning fork. Okay. Now in the second case, what we are doing is we are now dipping this under water. Okay. And now the same tuning fork, but it's in unison with when the beaker containing water is brought under the block, so that the block is completely dipped in water. This one vibrates in the 11th harmonic, but of the new system. Okay, so now this same frequency becomes, sorry, it becomes the 10th overtone or the 11th harmonic, but not of the same fundamental, because your tension has changed. Now your tension has become T prime, or it has become F10, but of the new system. So it is 11 by 2L, but square root of T prime by mu, and that is the same frequency as this one. Okay, so this is going to be 11 by 2L square root of mg minus buoyant force upon mu. So if you now compare the two equations, equation 1 and 2, you'll understand that 10 times square root mg is equal to 11 times square root mg minus buoyant force. So square both the sides and you'll get that mg is equal to 121 by 100 times mg minus buoyant force. So that means your buoyant force is becoming how much? Your buoyant force is becoming 21 by 100 times mg, isn't it? Something like this. So that means the density of water divided by density of the block is 0.21. So density of water is 1 gram per cc. So from that you will get. So 1 upon 0.21 gram per cc or 100 by 21. That will be the density of the block. Okay, so just note this down if required. Both the situations I've shown in the same diagram, but basically they're separate things. No. One time the weight of the block is creating tension, and that is creating a harmonic series such that your tuning fork is in resonance with the 10th harmonic or the 9th overtone. Next time the block is placed underwater, and that changes the harmonic series. But as it happens, the tuning fork is once again at this thing, you know. Just check my calculation once here, but up to this step it is correct, that 121 by 101. So you get 100 mg is equal to, oh sorry, this will be different. This will be by 121, not by 100. Yeah, okay. Because 100 mg will be equal to 121 mg minus buoyant force. So this will be by 121. So this is different. Okay, this is going to be 21 by 121. So density of the body will be 121 by 21 into 1 gram per cc, or you can say 121 by 21 into 1000 kg per meter cube. So it will be something in excess of 5. Okay, just go through the 57th question people will discuss. It's an important question. If you haven't done so far, then 57th question next. Just make the diagram and try to understand both the situations in that also. I'll explain it to you. said good talk. Now I'm back. My cat is sitting on my chair. Okay, off you go, Babu. Okay, so let us understand this 57th question properly. So क्या हो रहा है? एक time you have this assuming that friction is holding this thing from moving. So I'm not going to draw the whole diagram, but just explain the basic part of it. Yes, exactly. So क्या हो रहा है? One time when you have the junction or the knot between the heavy string and the light string suspended in air in between like this, that time that junction will act like an antinode because the other side of the string is this thing, it is light. So because of that reason, this junction will now act like an antinodal point as it vibrates. And I think he's given some hint like that also in the question about it. To explain that point, he's given some hint also. So of course the tension will be common, whatever the lighter strings tension, because they are both comparatively massless compared to the block that you are using below to suspend with. And so you're assuming there is sufficient friction to prevent any kind of motion in the system over here. So iska jo bhi weight hai, the suspended blocks, that is getting balanced by the frictional force at that end, and that weight is becoming the tension in the thread. So that will be a common value of tension. So that will be at the junction point, there has to be equilibrium. So there has to be same tension on both the sides. Okay, and that is getting balanced by static friction here. So when this vibrates, this string, it will vibrate in this kind of modes. For example, this will be the first overtone, or the fundamental would have looked like this, but whatever, this end will be node and this end will be node. So in this case, this will be the formula. If this length is L, oh sorry, my mistake, this is antinode. Yeah, so we just have to make a correction here because this is now suspended in air, so it's going to be different. Okay, so because this boundary of the string is attached to a lighter thread on that side, no? So what will happen is it will act like a flexible boundary. So this will be an antinode and this will be a node. So here, if this length is L, then the formula for modal frequencies will become fundamental is 1 by 4L square root T by mu, and the nth overtone is the 2n plus 1th harmonic of the fundamental, and the tension is equal to mg. Okay, so that's what it's saying. So the thread goes over the lowest frequency with which the heavy string resonates is 120 hertz. So this quantity is given to us as 120 hertz in this. Okay, so for this situation, our fundamental is 120. The first overtone will become the third harmonic. The second overtone will become the fifth harmonic, and so on and so forth, like that. That will be the series. But next, what we are going to do is we are going to shift this whole situation to one where this junction point comes right over the pulley. So it will become a rigid boundary point. Okay, so that is the point you have to understand from the language of the question here. That next up, when we shift this here by 10 centimeters, which is basically this length, so now what is happening is that the heavy string is basically stretched out between the block and the top of the pulley. So this is where the heavy string is. So it doesn't matter that there's a lighter string attached on that side, but it's resting on the pulley with tension. So that point will become a rigid boundary, or it will become a nodal point. Okay. So the same length of the string will now act as the length of a string vibrating in the harmonic series of one which has two rigid boundaries on either side. So this one's modal series will be according to that formula, the alternate formula. Okay. So same tension in the string, but just the nature of this changes. These are both nodal points. So here the fundamental frequency is now 1 by 2L square root of T by mu. And the nth overtone is the n plus 1th harmonic. Okay. So now if you compare, so this is a different series. So let's write it as prime. So if you compare this formula with this one, you can see comparing this equation and this second equation, you can see that the fundamental frequency in that case is actually equal to 2 times the fundamental frequency in this case, because wavelength is half, so frequency is doubled. So that means this is 240 hertz. Okay, so this series will now be 240 prime is, I mean f naught prime is 240 hertz. So the first overtone will become double of this. The second overtone will become triple of this. Okay, and so on and so forth. So this will be a new harmonic series, whereas this was the original harmonic series, because this was suspended in air at this point. So it was acting like an antinodal flexible boundary point. So that's one of the key things to pick up in this question. Okay, hope this is clear, people. Please let me know if there's any doubt regarding this concept here. How that boundary point is switching from an antinode kind of point to a nodal kind of point. All right, people. So hope you've written this down and this is clear. Okay, now let's see another type of more tricky version of this question, which is likely candidate for your JEE advanced type of exam. Now, this is another situation where basically what's happening is that not only we have the two boundaries at the end of the strings, but we also artificially create another boundary situation somewhere in between the thread or in between the strings. So let me explain with an example. So suppose we have a situation like this now, that we have what we have discussed till now, that regular kind of system where the string is having a rigid boundary at this end, and let's say it's having a flexible boundary at the other end. So that and all is normal here. Okay, but along with that, you also create another constraint artificially. So I'll explain how that happens. Okay. So this end of the string is rigidly attached to a wall. So this is a rigid boundary, and this is going through that, I mean, is attached to the ring, which is, in that kind of situation we have discussed. But in between, there is also a kind of thin wall somewhere, and the string is actually going through a narrow aperture in the wall. So imagine that kind of situation, that you actually have a narrow wall over here, and the string is going through a small aperture in that wall. So what will happen is that because of the aperture size being very narrow, that point will also by force become a node. Okay, so this is a rigid wall. Okay. Now let us say that the length of this portion is suppose 50 centimeters, and the length of this portion over here is 30 centimeters. The total length is 80 centimeters. Okay, and we have some other parameters. So again, this is a ring which slips freely on the smooth fixed vertical pole and all that. So all that is standard. All right, and also the tension in the string is known to us. Let us say it is this time 4,000 newtons, and the linear mass density is, let us say, 1 gram per centimeter. Okay. So now we have to find the fundamental frequency for vibration of the string and the formula for the nth overtone. So all this we have to find out. So the additional concept that we'll have to apply here is that other than the normal fact that this is a rigid boundary where the string is attached to the wall on the left hand side, and this is a flexible boundary and therefore an antinodal point where there's that ring and all that, there is also a third boundary condition that we are imposing, that this point where the string is going through that narrow aperture, that point is now forcefully becoming a node. So the standing wave pattern in the string will only support those modal harmonics where all three boundary conditions are satisfied, that these 2 points are nodes and that ring wala point is the antinode. So it's a 3 boundary value problem now instead of 2 boundary value problem. So this is the more tricky variation of standing wave patterns and all that. Okay. this has come very rarely in JEE advanced, but it has been seen questions like this, and you'll find some questions like this in your module and DC Pandey, etc. also. Just try this out. Okay, so let us understand, in any overtone mode what is happening. This point has to be a node and this point has to be a node, and also in this part simultaneously there has to be an overtone, so this point has to be an antinode. So the distance between node and node will be some multiple, so let's say n times lambda by 2. Okay, whereas the distance between node and antinode will be some odd multiple, so let's say 2m plus 1 lambda by 4. Lambda will be same on both sides because tension is same and all that. So lambda is equal to 1 upon whatever frequency square root t by mu. So let us first understand what modes it supports so that we know n and 2m plus 1. Here n and 2 m are both going from, n is going from 1 onwards, okay, and here m is going from 0 onwards. So let's solve this equation. So lambda is equal to 100 centimeters divided by n, okay, according to this, and according to that it has to be 120 centimeters divided by an odd number. Okay. So we can see that these two numbers 2m plus 1 and n have to be such that their ratio is 120 by 100, is it? So that is 6 by 5. Now see, this is not possible. Okay, because you cannot have the ratio of a even number and any number in an odd number and any number in general as 6 by 5. So this case here is not possible. Okay, show you another case where this is possible. So this particular case is showing that it's not possible. Okay, so this L1 is this much and this L2 is this much. Okay, now suppose we change the values of L1 and L2. Now next example, if I take L1 as, let us say, 60 centimeters instead of 50, and I take L2 as 100 centimeters instead of 30, then here what will happen, L1, which is n lambda by 2, will give us that lambda is equal to 2L1 by n. So that is 120 by n, and L2 is 100. So L2 should be an odd multiple of lambda by 4. So put L2 as 100. So lambda will become 400. That is 4L2 by an odd number. So hopefully this time we should get some solution. Okay. So 120 by n should be equal to 400 by an odd number. So the ratio of this odd number and this general number, natural number n, should be 400 by 120. Oops. Just a minute. I'll give you some values which are feasible. Okay. Wait, so change this. To 90 centimeters instead of 100. Okay, so let's see what we get now. Okay, so if you make L2 90, we will get this as, yeah, I think now it will give us something that makes sense. So it's not that what we did earlier doesn't make sense, it's just that those strings will not support any harmonics. But this particular case now, it will support harmonics. Okay. So the series will become such that for the fundamental frequency, they are the lowest values. So 2m plus 1 should be equal to 3 and n should be equal to 1. For the first overtone, this should be the next closest odd number. So it can't be 6, it will be, so 2m plus 1 should become 9, and accordingly n should become 3. Okay. And for the second overtone, this should be the next closest odd number, so it will become 5 into 3, become 15, and n will become equal to 5, and like that. And what will happen is that for the fundamental mode, L1, which is 60 centimeters, will be equal to n, which is 1 into lambda by 2, or L2, which is 90 centimeters, will be 2m plus 1, which is 3 into lambda by 2, lambda by 4, sorry. Okay. So either way, you can see you will get lambda as 120 centimeters. So you'll get the frequency. Four thousand divided by. This will be the fundamental. Now for the first overtone mode, L1 will become 3 times lambda by 2, or L2 will become 9 times lambda by 4. So either way, you will see your lambda will become 1/3 of this. Okay, so your frequency will become 3 times the fundamental. So it will become 500 hertz. Okay, like that, you have second overtone. So it's the other way around. F1 is equal to 3 times F0. So second overtone will become 5 times F0, or 2500 by 3 hertz. And like that, the series will continue. Is it clear? So you can see that the modal series is slightly different over here. It's still odd harmonics only, but you know how it looks. So in the fundamental mode, it will look like this: n is equal to 2. Sorry, n is equal to 1 means this side will be like this, and on that side, 2m plus 1 is 3. So there'll be 1.5 loops. This is how the fundamental mode will look like. Okay. Then the first overtone will now look like this. It's going to look a little complicated. There will be 3 loops here. And correspondingly, there'll be uh, 4.5 loops here. So you can see this is 3 lambda by 2, and this is 4.5 loops, or 9 lambda by 4, like this. Okay, so this is the first overtone. And like this, the series continues. Okay, people. So hope this question is clear. This part. So we'll conclude this session here today. Now we'll be starting with sound in the next lecture, but we'll also do some practice questions of waves in the next lecture, and then second part of the lecture we'll move on to sound. So yes, Ashwin, you can do that. Okay, you can send the doubts in WhatsApp, and we'll discuss some of the doubts I'll discuss in the lecture, whereas some of them I'll send you hints. All right, and also finish up any other. You can do questions from DC Pandey and things also, and you can send to me if you have any doubts. All right. So that completes, in principle, we complete transverse waves, though we'll have one more lecture of problem solving and doubts. Okay, that's it. Thank you guys. All the best.